Welcome everybody, whatever time of day, night it is for you. Here a second, I have to accept that. Welcome to the virtual seminar series of the IEEE ComSoc's Cognitive Network Security Special Interest Group. I am Shubha Subbalakshmi. I am a professor at the Stevens Institute of Technology. I am the chair of this CNS security SecIG group, which we started way back when, probably 2013 or 15. Professor Dola Saha is from University of Albany, and she is the vice chair who will be co-host today. And Dr. Charles Clancy from MITRE is also another vice chair. I will quickly try to introduce the SecIG, the seminar series, and our today's speaker. So currently we have around 223 members, all in the LinkedIn group. The SecIG can be found in the LinkedIn group, and that's your link there. You should be able to see that. You can also search for it under IEEE Cognitive Network Security Special Interest Group in LinkedIn, or you can send an email to either me or Dola. The SecIG virtual seminar series started mainly in response to keeping this group active during the pandemic, and this sounded like a best way to do it. We have had 5 talks, about 4 talks, and today will be the 5th one. The inaugural lecture was by Professor Winspoor from Princeton, and then we had a series of talks. Today it'll be Dr. Yalin Sagduyu from Intelligent Automation, Inc. And we have a few other speakers lined up for the next few months, so stay tuned, and we should have a pretty engaging rest of the year. So quick logistics. The recorded talks will be available at the SIG website. That's your website. It looks pretty long, but you will get an email soon enough. Here's just a quick sampling of what you will see and how it'll look like. And quick logistics of the talk. Everybody is muted on entry. Please stay muted throughout the talk. Feel free to type in your questions for the speaker in the chat. You don't have to wait until the end. You can continue typing if you think of questions on the way. We will read these things out at the end of the talk. Dola will be doing that, and our speaker will respond to those questions. So today's speaker is Dr. Yalin Sagduyu. He will be talking about adversarial machine learning for wireless security in 5G and beyond. He is the Director of Networks and Security Division at the IAI. He received his PhD in ECE from University of Maryland, College Park. At IAI, he directs a division of over 50 research scientists and engineers and executes a broad portfolio of R&D projects on wireless communications, networks, security, machine learning, adversarial machine learning, and 5G and beyond. He has been a visiting research professor in the Electrical and Computer Engineering Department of University of Maryland and College Park. He served as a conference track chair at IEEE PIMRC, IEEE Global SIP, and IEEE MILCOM, and in the organizing committee of the IEEE GlobeCom. He has organized and chaired workshops at IEEE CNS, ICMP, ACM Mobicom, ACM WISEC, and he has received the Best Paper Award at IEEE HST. So with that, I welcome Dr. Yalin Sagduyu, and take it away, Yalin. I'll stop sharing.
Thank you, Subha, for your introduction, and thanks to both Dola and Subha for your kind invitation. Let me share my screen. One second. Can you see it?
Yes, we can.
Yeah, all right, perfect. Try to move this. All right. Hello, everyone, and thanks for coming to this talk. As Subha mentioned, I will talk about this emerging concept of adversarial machine learning in the wireless security, and I will discuss several applications, including applications in 5G and beyond. So it's a mixture of the applications of machine learning to come and security in the wireless domain. And then we will talk about some security issues regarding the machine learning, and we will jump to the adversarial machine learning, and we will see how we can apply it to the emerging wireless systems. So I will say, start talking about a little bit about the wireless evolution. So, we are right now in the middle of the 5G area, and we are, heavily, moving towards 6G as well. And, with all this new advances, right now we can support higher rates, lower latency, and the number of devices we can support with this emerging services is continuously increasing. And right now we're also dealing a lot with the heterogeneous networks, and this will go, also be increasing with the 6G as well. And we will see how we will deal with all this ever increasing demand for connectivity and communication. So as an example, we will start with a little bit of a discussion about the 5G. There are new applications and services are available. And there are 3 examples in that case. And the first one is the enhanced mobile broadband. It is requiring a lot of a throughput support to sustain some applications like virtual reality, augmented reality, a lot of rate of communication is needed. And with the massive machine type communications, we have a lot of devices getting connection, and it is very important for different applications like smart cities, supply chains, etc. And there is another application called ultra reliable low latency communication. And the main point here is how we can reduce the latency to support these applications while we are having the high fidelity in terms of communication. And later we will try to see how we can map all these applications to some 5G specific issues, and then we will start discussing the security aspects as well. So the 5G ecosystem to support all these applications is very complex. It starts with some user equipment at the edge. You can have some autonomous vehicles. You can have some AR, VR handsets. You can have some drones, cameras, some gaming equipment, smartphones, etc. And they will all have some air interface to connect to each other, as well as to some base station. And this takes us to the radio access network. And then, the whole aspect is here is a virtualization of the different aspects of the RAN, and some of them will be handled by the multi-access edge computing, the so-called MAC. And then there will be some backend core support that will run some computational aspects there, as well as communicate across the different base stations. So it's a pretty complex ecosystem, and in this talk we will mostly focus on the air interface and the RAM part. And but a lot of applications we will discuss will also have some foundation as well to support a core network type of security issues. All right, and all these applications, and this complex ecosystem are supported by new capabilities offered by 5G. We are moving to millimeter wave and beyond. And now we are talking about terahertz for 6G. So the bands are getting larger, and there will be more available band, but it's coming with its own restrictions. We will have a lot of blockage, and it will be potentially easier to manipulate, as well as we are moving more to the AI type of aspects to support millimeter wave type of communication. And the same goes for the massive MIMO. We can also use the spatial diversity, and we can support a higher connectivity and communication demands with the use of the increasing number of antennas. And again, we will see a lot of AI aspects will be needed for that one. And another item, introduced for 5G we have seen before is the ultra reliable low latency communication, and this requires low latency edge computing as well. And another aspect I mentioned earlier, a lot of things in the 5G are being right now virtualized. We are talking about a virtualized RAN, and this all been done by the network function virtualization. So there's some kind of a trend to move from hardware type of implementation to the software level, more flexible implementation of communication blocks. And finally, all this application requires some a prioritized differentiated service. And this is done through network slicing that will provide some multiplexing of the different virtual networks across the same physical network. And we will see, different type of security threats for all this, parts of the 5G and beyond. And as we move from 5G to 6G, and this is right now the trend in the research community, now we are dealing with way more sophisticated systems. We are talking about a distributed computing, federated computing. We are talking about heterogeneous networks where satellites, drone, and terrestrial networks are all communicating with each other. And we are moving from millimeter wave to terahertz to sustain more rates, higher rates with the larger bandwidths. And there are some a new type of applications like hologram communications, and we are dealing with new type of communication type of tools configurable intelligence surfaces to sustain these rates and also deal with the new challenges introduced by terahertz and other communication aspects. And again, the AI will be a main part of this system because things are getting complicated. And there will be a need to orchestrate this complicated system, and we need to optimize this system using machine learning. And this takes us to the domain of machine learning here. And this concept has been there for many, many years. People have been talking from in 1950s, even before, about artificial intelligence, AI. Then they got translated to some algorithms, and they emerged as a machine learning. And for a while, it has been a little bit dormant because of the lack of the computational resources. But in the recent years, with the arrival of the computational resources, as well as with the arrival of the new data sources to analyze, deep learning has emerged as a powerful means to learn from the data and solve complex tasks. And the same applies for wireless communication as well. I mean, the main reason is twofold. Wireless spectrum data is very complex. We are talking about some heterogeneous type of systems. There are a lot of connectivity issues there. A lot of devices are being connected in the same a type of a network, but with different heterogeneous components. There are a lot of channel issues there, especially when we move to millimeter and terahertz. They are becoming very sensitive to blockages and other effects like atmospheric effects. There's a lot of traffic being pumped, and they're all coming with their own dynamics. It's a possibility of interference among the users within the network, as well as the jamming is possible as well. And there's a lot of mobility right now, across the network, especially with the drones. The mobility is becoming very dynamic and needs to be taken into account. So the data that is being produced by wireless systems is very, very complex. And also the tasks we need to solve in wireless systems are complex as well. So we can try to do some signal analysis using some analytical methods or some heuristics, but it is getting stuck at some point. We are dealing with terabytes of INQ data, and we need to analyze it to find some anomalies or try to understand better how to optimize it. And also the standard way of looking at the optimization problems in the communication design is a little bit changing as well. Right now, there's a lot of talks about how we can do a cross-layer design, how we can even get rid of the layers, and how we can do some a protocol waveform optimization. And those are again very complex because of all this channel issues and traffic and interference issues that are being introduced by the emerging wireless systems. So both the spectrum data is complex and the wireless tasks are complex. Therefore, we need to do something about it because the expert knowledge and the analytical solutions that we have been using so far cannot necessarily capture well the complexity of all these wireless channels, resources, and waveforms. And therefore, machine learning is emerging as some powerful tool to learn from this complex data and also help solve us some complex spectrum tasks. And here's a couple of application of machine learning for wireless systems. There's a lot of users that we need to understand better. We need to model them, and wireless the systems are again getting complicated. And machine learning can be effectively analyze the interactions between the users and to learn how to deal with this ecosystem of the wireless users. And it can also help us to shape the policy, how we access the spectrum in a dynamic way, and the machine learning is useful for that one as well. And there are a bunch of machine learning algorithms are available, we are customizing them to the channel access, beamforming, signal classification, and waveform design. And there are a couple of numbers. They are not necessarily very, up to date, but the number of publications we have been seeing in the machine learning related to the wireless is being steadily increasing, and the research is sort of moving how we can apply AI in a way to optimize the wireless systems. And also, I want to emphasize that right now, the community has been moving from conventional machine learning systems like a sport vector machine or decision trees to more like a sophisticated deep neural networks, namely the deep learning in that case. And the main reason is we have been, seeing a lot of algorithmic advances, in the last couple of decades, and also more importantly, computational advances are there. We have a lot of computational resources to support these deep learning applications. And equivalent importantly, we are dealing right now with rich training and test data sets. We have been using a lot of RF or other type of sensors that are creating a lot of data to analyze. And therefore, it is important to use deep neural networks. And also, it is pretty convenient nowadays. There are a lot of open source software, tools are available, and the community is pretty open to share the codes. And it is becoming some kind of requirement as well in the IEEE and other communities to share the data as well as the code when you write a paper, and they let you submit your data and software even to some databases there. All right, and deep learning has been used for different tasks, like a signal classification, trying to see, whether the signal is coming from one particular source or not, from particular waveform or not, etc. It has been used to optimize protocols, like in the case of MIMO communication. And also, you can use the deep neural networks as a funding blocks for transmitter receiver design in communication systems as well. And we can try to replace the communication blocks as some deep neural networks to do all the operations that we have been seeing, in the past. Sometimes it's independent and sometimes together. And with this introduction, I want to move to the concept of the adversarial machine learning. So far, we have seen AI has been used a lot for wireless systems, and the next question is whether we can trust the machine learning. And there are different aspects to that one. We can start with whether we can explain it, why machine learning is doing what it is promising to do. And also, there are a lot of issues regarding whether we can repeat or reproduce the results. So you can do some, you can get some results in the lab environment, but when you get to the field, it will work or not. And it's also tight whether the, radio hardware, is possible to replicate, whether we can get, rid of all the uncertainties in the wireless channel and we can exploit them to optimize the system. And whether we can also have some kind of confidence and robustness when we move from training to testing. It is not well understood yet. And another aspect here is the adversarial machine learning, and we will see that this machine learning itself is very sensitive to some manipulations, and we need to basically be careful and try to protect the machine learning core of the systems, including wireless. So we will start looking at the security vulnerabilities of machine learning now. And one main reason why it is vulnerable is that the decision space of all this machine learning, deep learning is getting more and more complicated. So we are looking at some complex decision spaces that are being very, fine-tuned against the training data, and it is possible to manipulate this decision space by giving a wrong inputs in the test time or in the training time. In this way, we can fool the system to make into a wrong decision. So deep learning in particular, because of its complexity, is very vulnerable to attacks, and we will see these attacks in detail next. So the whole concept of adversarial machine learning is trying to understand how we can learn and protect this learning in the presence of an adversary. And here's one canonical example coming from computer vision domain, where most of the development has been done. And we have one image classifier. It can be in the cloud, and one image is being sent. There's a test input. It's a panned image, and it is giving a correct answer. In terms of a label. But if you put a very small perturbation onto this panned image as a noise, but very well crafted one that cannot be detected visually, then the image classifier is being fooled and it is giving the wrong label, like a given. And the whole attack is called here the adversarial or the so-called evasion attack. And the idea is to fool the classifier into making wrong decisions. And in the meantime, we need to make sure this perturbation we are adding is pretty small so that it cannot be detected. So here's some mathematical details. I will not talk too much to that one, but we are dealing with some classifier which is being trained with a parameter set. And the idea here is to minimize some loss function L there and given some training data and true labels of this data. And the problem of the adversarial attack is how the adversary selects some perturbation there for any given input. And the goal is to minimize the strength of this perturbation. And there are some constraints to that one. First of all, this perturbation should be small. This is the the last constraint here. And the other constraints are coming from the type of the attack. If you want to make sure that the label needs to be changed in the attack to a particular target label, then we are talking about the target attack. And the idea is the classifier is giving, as a label, one like a target label, which is not necessarily the same as the true label. And another attack is the untargeted attack. As long as it is not the true label, then you can misclassify, you can enforce the the classifier to any other label. So we are dealing with two types of attacks here: targeted attack to a particular label and untargeted attack. To solve this optimization is hard because of all this non-linearities, etc., involved in this complex decision spaces in the neural networks. And this is by default a non-convex problem. And therefore, we need to some kind of find some approximations. And one way of approximating is approximating the loss function. And we are trying to linearize it, writing it as the original loss function plus some perturbation added some gradient there. And it is taking us to some gradient methods type of finding these perturbations. In the targeted attack, again, we want to minimize the loss function to a particular target with respect to a particular target, such that the system as a deep neural network will select the particular target as the label. In the R-targeted case, you want to attack the whole system across all labels. Therefore, you want to maximize the overall loss function. And again, we have some parameter there we need to set to satisfy this third constraint we have seen before in terms of the strength of the perturbation. And there have been, a lot of work have been done, and different methods have been proposed, and there are some kind of variation of each other. And most of the time, we are dealing with either like FGM or some variations of it, and most of the results here will be based on the FGM. And these applications, have been studied in different domains. For instance, in the autonomous driving, you can, try here to fool the system such that the car will think that the autonomous car will think that it is like a stop sign or like a speeding sign, although it is not the case. In the voice applications, you can try to fool the Siri by whispering some like a tone there, which cannot be really heard by a normal user, but the Siri will catch it and will translate something to wrong. And also, we are seeing some like a text classification applications. We can give it to a text classifier some text that will give you a negative as a label, and you can change a couple of words or letters there, and it will become positive now. All right, now how we can apply to wireless systems will be discussed in the next slides. Right, so first of all, wireless medium is open and shared, and you can eavesdrop it. You can try to infer what is going on in the communication, and you can also try to jam it and manipulate the ongoing transmissions as well. And there have been some studies, of course, in the eavesdropping and jamming, literature, and a lot of it has been done to protect the system, and but they are not necessarily effective against adversarial machine learning type of attacks. And we also want to point that there are some unique characteristics in the wireless systems due to the channel, interference, traffic, and spectrum sharing that are not necessarily available in other domains like a computer vision or natural language processing. And it is giving, it is making this attacks and defenses also more complicated. So in the computer vision, we can simply add a, a perturbation to a panda image, and you can send it to the classifier. but you need to do it over there in the wireless system. So you cannot really like add a perturbation right at the receiver. It needs to be transmitted over there. And also the signal that is being, normally, reaching the receiver is also coming to the, the channel as well. So here we have the H1, H2, and as the noise, and H1, H2 are the channels. Those are sort of like giving some uncertainties that we need to deal to attack the system as well as to defend it, right? And also what the victim system and the attacker are seeing are completely different because they are observing the spectrum in a different way, potentially from different distances from the emitters, seeing different channels. And also their hardware could be different as well, so that there will be some variations in terms of how this, the RF signals are being shaped when they are received. And also it is not possible to manipulate the input to the receiver where the classifier resides directly. The attack needs to come over there. And here we see an example. There's one transmitter transmitting different signals with different modulations, and the receiver is receiving some INQ samples, and those are the features, and the label is the type of the modulation, and the receiver is trying to classify it. And the adversary transmits a perturbation over there, and it is reaching the receiver with by experiencing a particular channel there, HAR. And the HAR times delta is the perturbation, added to the signal, and it is, aiming to make the, the system fooled into selecting a wrong modulation. And this problem is becoming complicated because of the channel characteristics there, and you need to, take into account this channel characteristics. And now the problem is being changed in the course of optimization to the following. Here we have this additional item in terms of the, the perturbation received over the channel. If you don't take this, into account, hello? Yeah. If you don't take this, perturbation, experiencing the channel into account and attack without this channel, then, the performance is very bad. The system has a good accuracy, under this attack. But once we have this channel into account and take this, into account on all the optimization, the performance of the classifier starts dropping as we start increasing the strength of the perturbation there. So it is very important to take into account the unique wireless characteristics when we design this adversarial machine learning attacks. And the next question is how we can protect the system against this attacks. So the one idea is to make the classifier itself robust against perturbations. And there are different ways of doing it. And one way is doing the adversarial training. While we are training the classifier, we are also creating some adversarial examples, and we are adding them, during the training, so that the training itself sees these adversarial examples, and they are trained to deal with them as well. And another way of dealing with this robustness issue with the classifier is to enrich the training data. We can augment the training data by adding some noise samples, and this way the classifier will see different enrichments of the training data, and it will become more robust when it sees in the test time. And when we apply this defenses, then the accuracy of the classifier start increasing. The red one is without the defense. The accuracy starts dropping as we increase the the strength of the perturbation. And even with a small one, we start seeing some drops. And when we apply the defense, then we can start maintaining a little bit higher, accuracy. But again, more, defense approaches are needed for that purpose. Another, concept in the defense against adversarial machine learning is called the certified defense. So the people are trying to certify their defenses in terms of their performance in test time. The idea is whether we can guarantee the classifier robustness against these perturbations, but most importantly, the test time, not only focusing on the training time as well. For that purpose, we are applying randomized smoothing, not only in the test time, but also not only in the training time, but also in the test time. And, for every test sample, we are augmenting it with some noisy samples, and we are building some kind of augmented, set of test samples, and we are giving them to the classifier that has been already made robust by the previous methods. And then we, get some like a set of results for different augmented, samples there. And then after that, we apply some statistical significance tests, in particular some hypothesis tests, to check whether the results, given by the classifier in terms of label are statistically significant or not. And we can also enforce some confidence and say that, hey, with 90%, this defense is certified, or 95%, this defense will give us the wrong, correct labels. We will, sort of like flip the wrong labels. So those are some like defense methods that we have been applying to protect classifiers in the virus domain. And so far, we have only seen the adversarial, the so-called evasion attacks. There are many attacks here, and we will try to visit them one by one and try to see what we can do in terms of like a wireless attacks and how we can, defend them against this kind of attacks. Right, and those are the inference attacks, poisoning attacks, Trojan attacks, and some attacks that are most on the private side that are trying to infer some characteristics of the deep neural network as well as the data involved in the training and testing of this deep neural networks. So we will start with the first attack, exploratory inference attack. We have some classifier there. It could be black box or white box, but let's start with some black box attack. You are sending some images there, and you can send it, as many as you want, and it can give you some, results. And this way, you can build your own training data set, and you can train another like a deep neural network, and this may give you some similar results as this black box classifier. And the whole idea here is building a surrogate or so-called shadow model, and it is very critical in many attacks because we will not have an access to the black box nature of the classifier. We will need to build our own surrogate shadow model, and this model will become like hopefully functional and statistically similar to the original classifier. And then we can analyze this, the surrogate model to find some weaknesses of the classifier that we are attacking. And the next attack is the causative poisoning attack. So this is an attack in the training time, or if you retrain the system, it can be done as well. And in several cases, data is being collected by different sources, like using crowdsourcing or other methods. And some malicious users can try to inject some manipulations to the training data. And the adversary will try to modify some labels of the training data samples, not many, but a few of them. And then the trained or retrained model then will become poor in terms of giving the correct answers when it is used in the test time. So this is an attack in the training time, and it has a lot of applications in the spectrum sensing and dynamic spectrum access. And as we know that lots of the time we are using like a cooperative spectrum sensing and other methods to collect sensing results from different resources, and we will try to combine them to make one final decision. And here we can see some applications of these attacks in the dynamic spectrum access. And in a very a simple summary form, the idea of the DSA is to sense the spectrum and try to access it, either if it's idle or if it is okay in terms of maintaining a good performance and you are not interfering with the primary user that is sort of owning the channel. And for that purpose, we can launch an inference or exploratory attack. The adversary can sense the spectrum and train a surrogate model to mimic the transmit behavior of the dynamic spectrum system. And it will learn when the system will try, when the users will try to access the channel depending on the sensing results they will see. So it is sort of building a surrogate model for spectrum sensing part. And this surrogate model can be used to predict when there will be a successful a channel access. And then, again, it can be used to jam the data transmissions that will be otherwise successful. So it's just taking us to the second inference-based jamming attack. And it's also possible to, launch an evasion attack. You can try to jam the spectrum sensing period rather than jamming it fully, in a bold way. You can also try to do it in a very stealthy way. You can, jam, insert a very small perturbation to the system. And during this perturbation, the spectrum sensing results will be very slightly, be manipulated, and later it will be, caused to make some wrong channel access decisions. And we will see some results related to the 5G later. And finally, we can, launch a causative poisoning attack in the training time. And it is possible that, the spectrum sensing period is being used to collect data, and then you train a classifier or retrain it to access the channel, and you can try to manipulate again over there, identify some small perturbations that the system will think it is like a little noise edit, or it may not be understand because it will be around the noise floor. We have seen some curves there with some like a perturbation to noise results that are in the like a minus, like a PNR level. So they will be very small. They will be hidden in the noise, but it will make the spectrum sensing results, like manipulated. And there are two other attacks that I have, shown earlier in the chart there when I summarized the type of attacks we have. One of them is the Trojan or backdoor attack. It is like a mixture of an attack that you need to launch both in the test and training time. And so the idea here is you want to poison some training samples, but not all of them, as it in the poisoning attack. You want to like add some triggers. You need to add some like a small characteristics to some like a data samples, and then you need to only flip the samples, the labels of these samples. And in the wireless case, it is possible to make this attack over there by, like sending some perturbations later in the test time that will, change the phase shifts of the received signals. Therefore, it is possible to add these triggers in terms of like a small phase shifts. And then later we can activate it over the air, by adding these phase shifts in test time. This is very relevant right now because the community is like using a lot of data available online. For instance, you can like push some data that has Trojans in it, and later you can activate this data, and you can make the system make some wrong decisions in test time. And the next attack is the membership inference attack, and here the idea is to infer whether a signal of interest, in our case a data sample, has been used to train a classifier or not. The idea is to learn more about the classifier such that we can later analyze it to understand what are the waveform, device, and channel characteristics involved there. And we can use all this to generate the signals, because we know that what kind of signal has been used to train a classifier. Later we can use this information to generate similar signals, and we can use it to infiltrate, for instance, a user authentication system if like a machine learning type of a classifier has been used to authenticate users in the physical layer. And again, we will see some results related to the 5G. Now, let's move how we can apply this concept of the adversarial machine learning, not only like in the standard cognitive network type of security, but as well as in the 5G and the emerging, communication systems. And we will go through some, types of attacks here. There are 6 of them. We will go one by one, and we will see, what kind of adversarial machine learning effects we can observe there. The first attack is on the spectrum sharing of the 5G. As we know, the 5G is requiring some like a bandwidth to support all these applications, and this spectrum is very crowded without any like availability right now, and there's a lot of like users using these bands. There are some incumbent users like radars using these bands for their own operations, like in the CBRS band. And right now the trend is to open these bands to be used by commercial users like 5G. And to be able to do that, you need to use some kind of a machine learning to understand whether this incumbent user is there or not, whether, for instance, in the CBRS band the radar is there or not. And then you can like try to identify the the time when you can use the 5G, or when you need to back off from a particular frequency. And therefore machine learning is being used, and therefore it can be attacked as well. Another way is like using machine learning in 5G is like using it for authentication of the signals. As we have discussed before, there will be many devices accessing to 5G services. Therefore it will be important to authenticate them. And as we know, password-based solutions are not necessarily very protective, and therefore people have been looking at some physical layer aspects that they can use to authenticate the signals and the users behind that. And again, machine learning can be used and can be attacked as well. And also, machine learning can be used to detect whether there is a rogue 5G signal, because you can launch an attack to establish a covert 5G signal. And also, in the fourth case, we can also use machine learning for some advanced communication, schemes that have been used by 5G and potentially 6G. As we are moving into millimeter wave and terahertz, it will be important to select all the beams because of the narrowness of all these directional transmissions. And again, machine learning is being used for beam prediction, for initial access, and again, it is possible to attack it. And the last two attacks, the fifth and sixth, are related to the 5G RAN slicing. We will see how we can, jam it in an effective way so that we can mess up with the resource allocation for 5G RAN slices. And we will see how we can also launch some flooding attacks, like the TCP/SYN attacks, but now for the 5G RAN slicing. So let's start with the first attack there. We are talking about adversarial machine learning for a spectrum sharing. And we are looking at the CBRS band at the 3.5 gigahertz, and it is reserved for federal use, in particular by radar. And recently, this band has been opened to be shared by commercial users, such as 5G. There have been some auctions going on, and people start getting bands there, and they will start operating some 5G private networks there. And they need to be careful because there could be some still incumbent radar usage there, and some kind of environmental sensing capability will be needed to detect the incumbent radar signals. And as we know, deep learning is very powerful to analyze this kind of signals at the INQ level that has been captured over there, and it can try to identify whether there's an incumbent radar or not. If it is the case, then the spectrum access system SAS needs to reconfigure and manage the whole system such that it can coexist with the radar system. And here we can see some a simple diagram there. The ship here is equipped with a radar, and there's some kind of environmental sensing capability as a receiver there. If it is detecting a radar, it will tell the SAS spectrum access system, and it can reconfigure the 5G so that 5G can operate without interference to the radar. However, it is possible to launch an attack to the environmental sensing capability as well. The adversary can sense the spectrum and learn what's going on in terms of the transmissions, and train a surrogate model to predict when there will be some successful 5G communication, and it can then try to transmit some perturbations. And the idea here is to fool this environmental sensing capability into misclassifying radar signal. While there's a radar signal, the ESC will think there is none, and then there will be interference between the 5G and radar, or the radar system, or the ESC will think that there is a radar, and it will sort of tell to sort of vacate the frequency band, but there is no radar there. Then there will be some kind of a waste of the opportunity, and in terms of the throughput and the other performance metrics. So this kind of attack, is pretty effective, and we have shown that, it's possible to reduce the 5G rate, a lot compared to a conventional jamming. First of all, conventional jamming is easy to detect, and it is using a lot of energy, and it's also not necessarily very effective because it is putting all this noise over the whole band and signal characteristics, and deep learning can learn to deal with that, although it is very sensitive to this adversarial perturbation that we craft very carefully, as we have shown in the other classifier examples. So the second attack is about whether the adversaries can set up some covert or so-called rogue communications in some unauthorized places. So there's one a user there, which is a rogue user. It wants to communicate, but it shouldn't be detected by the spectrum guard there. And for that purpose, it can either add a perturbation on its own signal, such that this G0B base station can receive it, and the spectrum guard will not be able to detect it. Or it can also use a separate aid there, and this can be formulated as a cooperative jammer. It will transmit this perturbation separately, and again the idea is to fool the spectrum guard, and the idea again here is to hide the 5G signals below noise floor. And very important, we should still be able to sustain high data rates. And to be able to do that, we need to take into account all the channel characteristics, from the transmitter to the base station, so that we can sustain a good rate, as well as the channel from the the transmitter to the spectrum guard, so that we can fool it. And this way we are adding these perturbations, and the spectrum guard cannot detect the rogue signals. And in the meantime, the GNOP can still reliably receive the rogue 5G signals. There will be some drop, but we show that the increase in their rate is limited to the 1%. And the covertness such that the spectrum guard cannot detect it is more than 95%. And it has been done by adding a perturbation which is way below the noise level, like left minus 5 dB. So the third attack is about the authentication of the users to access the spectrum. And as we discussed before, it's possible to protect the system by adding some passwords and other methods, but those are possible to crack at the cyber level. So people have been thinking, since there are so many devices that need to be connected to the the 5G, and they are not necessarily all of them very smart, probably they are very cheap devices. So whether we can authenticate them by looking at their physical layers, characteristics. And this physical layer signal characteristics include the waveform characteristics. They need to use this right waveform, as well as some hardware characteristics, because the hardware will also introduce some effects on the signals as well, received by the GNOP. And these effects include frequency shifts and phase shifts, and it is related to the oscillators used by these devices, etc. And the idea is GNOP can try to use some deep neural networks and apply them on these received signals and try to authenticate the users and as legitimate or not. And the idea of the adversary is to spoof some signals and try to bypass the authentication system that is based on deep learning. And for that purpose, we have been using a generative adversarial network, the so-called GAN. And GAN is a very useful, concept to generate some synthetic, data samples that, look and feel like the original ones. And it consists of two deep neural networks. One of them is the generator network that is generating synthetic data, and the other one is a discriminator network. It will try to discriminate between the synthetic data generated by the generator network and the real data. And both the discriminator and generator are deep neural networks. And of course, there's a game between them. As a discriminator is getting better, generator should be getting better as well, and vice versa. And you sort of set up it as a game, and they play it in a sequential way, and they converge to some equilibrium such that both the discriminator and generator are trained to work very, very powerfully, and then we can grab the generator and spoof the signals. So this concept has been heavily used in the computer vision domain. Now, what is the difference in the wireless? There are two things. The first of all, the data both to the discriminator and generator, we cannot manually input them right in the computer vision domain. So they will come through some channels. So although you can generate something like a generator, it will come over some different channels, and they need to be discriminated using also this channel effects. Second, discriminator and generator, they need to reside at different places. The generator needs to be at the transmitter of the adversary, and discriminator will be used at the receiver of the adversary. So they need to be physically separated as well, and all the operations needs to be done over there. So this is taking us as to this over-the-air GAN concept. The adversary transmitter is acting as a generator, adversary receiver is acting as a discriminator. And we are putting some adversary receiver, close to the GNOP. Adversary is sending some signals, CUEs, the legitimate ones are sending some signals, and the adversary receiver is learning how to distinguish between them, and it is sending a 1-bit type of a feedback to the adversary, whether it can detect or not. And this way, the generator and discriminator are being trained. And after that, in the attack case, in the test time, the adversary only is using the generator, and it will, generate the spoofed signals. And these signals will be, taught by the GNOP as the legitimate signals, because the deep learning classifier at the GNOP will be, fooled into making these errors. And we show that by, depending on the signal strengths we are putting here and there, the attack success can be very, strong. For instance, if we are putting the adversary transmitter, only operating at the 3 dB, it can, fool the GNOP by 90%, and only 10% of the time it will not be authenticated. Right. So this was the third attack. And we also want to talk a little bit about the defense schemes, and this defense can be applied to the previous attacks as well, but I want to talk in particular for this example. So, what the defense is doing is to prevent the adversary from building a reliable surrogate model. All these attacks are, based on the adversary listening to the spectrum, capturing some over-the-air signals, and some kind of like trying to understand the mechanism in the communication system and building a surrogate model such that it can, craft some like adversarial attacks. And to be able to prevent that one, the defense can be set up the following way. The G0B can make some errors in their decisions. It can, deny access to some legitimate real users, and this denials can be done in a very few times. So these errors are very few typically, and also it is not necessarily affecting the system too much because you can immediately send another request and it can be, authenticated as well. However, the adversary is like observing this, mechanisms over there, and it will be fooled because some of the time G0 is making some mistakes. And as we start increasing this errors, if you don't introduce anything, the attack success is very high. If you introduce a little bit, then the attack success is still high, so the defense is not enough. But if we introduce too many errors into our like authentication system, then the authentication system itself is start making mistakes. So you don't want to add too many errors. So you need to sort of like find a balance and try to introduce a small number of errors that will reduce the attack success. But in the meantime, you should be able to still like authenticate the legitimate users most of the time. So this is sort of the defense in terms of preventing the adversary from like building a reliable surrogate model. So the next couple of attacks we will talk are very specific to 5G and other schemes that are communication systems that are heavily using machine learning and in particular deep learning. And as we discussed earlier, these systems require a lot of like a bandwidth, and millimeter wave and terahertz bands are providing this bandwidth. However, as we start increasing this frequency, then we start dealing with narrow beams, very directional transmissions. And it is causing us a problem in terms of the user equipment and the base station G0B finding each other, even before establishing the connection. So in particular, in many systems, including some Wi-Fi systems and 5G, the UE before connecting to the 5G, 5G network, it needs to establish the initial access with the base station. For that purpose, the G0B is transmitting pilot signals over different beams, and those are very narrow beams. And the UE has a omnidirectional receiver, and it's computing the strength of the received signal for all these beams and finds the best beam. In other words, we need to do the beam sweeping across all beams, and it is taking a lot of time because we are dealing with a lot of like narrow beams to cover the all like the domain there. And the question is whether we can reduce this beam sweeping time, because we should have some time left for data communication too, right? And also the 5G standard is also like emphasizing and putting some kind of a constraint in terms of how much time needs to be spent on the initial access. And therefore, we try to answer the question whether we can reduce the number of beams swept. And for that purpose, the G0B transmits on a small number of narrow beams, let's say only 4 beams. And the UE computes the received signal strengths for this small number of beams. But it uses a deep learning classifier to predict, to select a beam from a larger set of beams, let's say 24 beams. So we have a deep neural network, which has an input like a small number of beams, let's say 4, and the output can be from a larger set of beams, 24. And this way, we only need to sweep 4 beams instead of 24 beams. And you can show that this kind of a deep learning classifier has a very high accuracy, and it can find the best beam. It doesn't need to be one of these 4 beams. It can be one of any of these 24 beams. So the next question is whether we can fool the system into making mistakes, because all these operations are done over there. So it is possible to fool the system. For that purpose, the adversary transmits perturbations during the initial access, and the idea is to manipulate the received signal strengths on different beams that are all being input to the deep learning classifier, and this way the accuracy of the beam prediction drops significantly, and the attack is way more effective rather than jamming it with like a Gaussian noise or uniform noise. and also you can, you don't need to transmit with full power. These adversarial perturbations, are having like a very small power as we put some constraints on it. And finally, I want to move to the 5G radio access network slicing. I mentioned a little bit earlier that we need to use different services, and we need to secure them, prioritize them to have access to 5G. And some of them require, a broadband access. Some of them require a low latency, and we need to also secure them and prioritize them, as well. And it is taking us to the concept of the network slices. And we also need to allocate resources, both RAN communication resources as well as the computational resources to support these different services in different slices. And all of them will be some virtual networks residing on the same physical network. And this is part of the near real-time RAN intelligence controller, where we make the decisions for the resources. And each user equipment sends some request with required resources, priority, deadline, etc., to start communication. For instance, if you want to use some VR, AR type of a capability, it will say that I need high, throughput volume, I want low latency, etc. And then the G0P, needs to decide whether it is okay to accept this request depending on the availability of the frequency band and computational resources, and what resources if it should be allocated. And as we allocate resources to some users, they will be blocked for a while and they will not be available. So therefore, the resources and all the decisions are, correlated over time. Therefore, we need to learn it over time as well, and model this reinforcement type of systems are useful to learn, how to adapt to the traffic demands and channel conditions and availability of the spectrum. And in this reinforcement learning agent, the state is the available resources. The reward is the number of the accepted requests, and the action is to accept the request and allocate resources. And this way, we can use a machine learning, and we can allocate resources, over time. And we show that it is way better than using some standard methods like a myopic type of optimization, or using some more like a random type of a resource allocation. And we can sustain, a different number of users with this, reinforcement learning that can be implemented as a Q-learning or as a deep Q network. But, this kind of a resource allocation for network slicing is also, susceptible to attacks. You can try to jam it, and you can try to, manipulate this resource allocation problem there. And very important here, we are not trying to jam in a bold way the frequency blocks. The whole idea is to fool the reinforcement learning agent here. Namely, we are attacking the machine learning core of it. So here the idea is the jammer, the adversary jams some of the 5G resource blocks, and it is trying to build a surrogate model over the air again, trying to learn how this network slicing, resource allocations has been done. For that purpose, it needs to just follow what the resource blocks are, empty or not, by using some a spectrum sensing classifiers there, and it will try to see whether a transmission is starting or not. And the goal of the adversary, by using the surrogate model to identify when and how to jam, to maximize the number of failed requests. So the request should not be, admitted. And during this attack, the reward is becoming smaller, and the 5G piece reinforcement learning will adapt to that one, adjust the reward table, and sort of there will be some kind of a game between the the reinforcement learning agent of the adversary and the 5G. And a very important fact here is that the reinforcement learning algorithms cannot recover easily even after the jamming stops, because it will take a while for them to learn how to adapt. And even after, let's say before the attack, you have some a reward on the average, and the jamming, it starts dropping. And whenever the, jamming stops, the reward still, keeps dropping for a while. And then after, it will learn how to deal with it, and it will come back. And this gives us some kind of a recovery time there. And it is this recovery time is very long, and during that time, the 5G network slicing will not perform as before. And we show that this way we can reduce the 5G rewards significantly under this attack. And again, it is better than other a type of simple attacks. And this not only works for network slicing systems based on the reinforcement learning. You can also launch it to the ones that are using myopic or random systems. And this kind of attack is helping you to reduce the reward overall. Right, and so there are a couple of ways of defending the system. One way is to protect the reinforcement learning from the effect of the attack. The idea is whenever you sense there's an attack, you can stop updating the reinforcement learning agent and wait until the jamming attack is over. So it really depends, whether you can detect this attack or not. Since the jamming signals are having very small perturbations, it is not necessarily the best way to go because you will make some errors and you will stop the updating even there is no attack. And another way is to try to prevent the adversary from building a reliable surrogate model. So while the adversary is building the model, it will require some a reliable data to train its own RL model. And again, as we have seen before, the defender can introduce some randomness either in the RL decisions or play with the decisions being done in the network slicing handshake, and it can try to fool the adversary as well. And we show that this defense reduces the impact and also reduces the recovery time by 50% compared to the case where we have the full attack. And the final attack I want to talk about is again related to the 5G, RAN slicing, and this is a flooding attack. The analogy is the TCP SYN flood attack, where you send some request to open some TCP sockets and then you don't use it. And in the same way, the adversary can start, sending some fake requests. And the idea is you send a request, let's say for VR AR application, and you don't use it later. So the idea is to start the resources available that will be otherwise available for real requests. And again, it starts with building some surrogate model from the adversary side, and then the adversary decides based on this surrogate model which resources to ask for in this fake request. And again, this fake request should be accepted by the system. So you should not ask for many resources, otherwise you will be detected or rejected. And also fake requests should block as many resources as possible. If you send few requests, then it will not cut. And this attack is again very effective, and it can reduce the the reward of the real request. It will not reduce the reward of the whole system because some of the rewards are being given to the fake requests. But it will reduce the portion of the rewards given to the real request. And again, this example shows that it is possible to attack the machine learning component of a system, in this case, the 5G RAN system. And it is possible, to, cause a big impact. And this impact is more than the benchmark attacks, that are using either a random methods or some a myopic optimization methods, etc. And this takes me to the end of my talk. So in terms of conclusion, I want to emphasize that machine learning finds a lot of use cases in wireless communications, as we all know, and 5G and beyond in particular benefit from machine learning as well. And this is sort of the trend going to the 6G, where we will expect to see a lot of AI components. And as AI and in particular machine learning is being used by these communication systems, the machine learning itself is becoming susceptible to attacks, and therefore adversarial machine learning generates a new attack surface for wireless communication. And to deal with that, more work is needed to understand this attack surface. We need to find more vulnerabilities in the system, and also we need to focus on providing some defense methods as well. All right, so this is the end of my talk. Back to you, Lola.
Thank you, Yalin. It was a wonderful talk, a lot of information for all of us to process, but let's first start with some of the questions before we move on. So the first question comes from Hisham Muhammad. He's saying, in the poisoning attack, how do we define the confidence level for the classifier to the training data, since the classification is based on probability between multiple classes?
Yeah, so that's a good point. So yeah, so you will have different classes, different labels, right? You can try to poison the data of a particular label on it. And so this will hopefully have more effect. But as the classifier is trained by building this decision space for all these labels all together, it will not necessarily give you too much of a confidence there. Again, while you are writing all these equations, because there's some math behind it, I skipped for some of the attacks. When you write to optimization, then the loss function that you are trying to fool or manipulate, you need to sort of do it with respect to a particular target. We have seen in the evasion attack, we are sort of manipulating the loss only with respect to one target. So you can try to do it in the poisoning attack as well. But if you want to have an effect of a particular samples of a particular label, then maybe Trojan is better. So you need to introduce some characteristics in terms of triggers as well in the data for a particular label. Not only modify the label, but also play with the data, the feature as well.
Great, thank you. So the next question comes from Jeff Reed. And I believe the question is about slide 33, where you have described all the attacks, possible attacks. So he's saying perhaps another attack is against the scheduler.
Against where?
33,
okay.
I believe.
Okay, scheduler. Yeah, definitely. By the way, hi, Jeff. So yes, it's possible to attack scheduler as well. I talked a little bit about the RAN, near real-time RAN intelligent scheduler. So it is possible to attack that one because we want to have some AI in it to make some decisions how to use this a virtual resource blocks. I mean, we discuss it in terms of the network slicing, but it doesn't need to be, within the network slicing concept. So, for instance, people have been using ORAN or other, a software development efforts to end up with some scheduling algorithms there, and the machine learning will be definitely used there, and you can manipulate that one. So, especially ORAN is a type of open source, is very susceptible to these attacks. Some people can, claim I train a model and put it there. They can put a Trojan in it. They can, train it in a way that it will be poisoned as well. And also, if you know how the scheduler is working, again, we can try to manipulate it over there as well. So that's a very good point. Yes, scheduler is very, very susceptible to these attacks.
Yep. So the next question comes from Manoj Banugondi Rajashekhara. Nice talk, Yalin. Thank you very much. My question: what is your opinion about adversarial attacks, evasion, on a regression setting in wireless system? Is it possible for the adversary to attack a regression-based wireless system? Could you give an application where this can happen as an example?
Yes, yes, it can be done, and we have been working on that one as well. Not every machine learning algorithm is being used, to end up with some discrete set of labels. Some of them are for the regression models, and the communication system, can be used for that one as well. For instance, examples are, I guess, abundant. If you want to do some kind of a rate control, rate splitting, you are splitting the rate in a continuous way, and it is a regression, right? So this is one example, for instance. And some other things, if you want to split the frequency to access the frequency, right? And people are, talking about how we can, split the frequency and then sort of put them together, right? In later. So again, how we divide the channel into some pieces of frequency. Again, it's a continuous problem, could be. And again, you can apply some regression. So there are, a bunch of examples of a regression style machine learning in wireless communication, and it is possible, depending on the system, to manipulate an attack. Again, it will be the same way. You will add some a perturbation there, and the loss function, the regression, will be a little bit different. But again, it will be about maximizing or minimizing the loss function depending on target to non-target.
So the next question comes from SKK. When retraining or implementing defense mechanisms for the neural networks, in what cases are either black box or white box attacks preferred to train against? What are some examples of situations where perhaps a black box attack would be preferred to help retrain a system?
So Can you read the first part again?
So when retraining or implementing defense mechanisms for the neural networks, in what cases are either black box or white box attacks are preferred to train against? So that's the first part of the question.
Okay. All right, so we are talking about like a training type of attack. So it is more like a poisoning type of attack, right?
Right.
I mean, so again, I mean, white box attacks are, I mean, like I don't know, on the paper easier to attack because you know more about it. To be able to do black box attack, you need to have some kind of a surrogate model. If you don't know much about that, it will be more difficult. So I think if you have a white box attack, it is, I mean, system, it will be more preferable to attack in the, yeah.
And the next question that is related to this is, what are some of the examples of situations where perhaps a black box attack would be preferred to help retrain a system?
Yeah, so that's so I mean, yeah, so I don't fully get the question because I mean, in terms of attack, I don't know how it will help you so to train the defender system. But if you are talking about training the like a attacker system in terms of a surrogate model, then black box system may be sometimes useful because if you are doing some kind of if you know all the white box, everything in it, and you try to train with additional data from the attacker point of view, it is possible that you will do some overfitting. So you will train to the point of all this data and all this like a, you know, like a little like things in the decision space, and in the real life, the channel, etc., will be different, and you will like end up with a bad performance. So therefore, you know, if you have a black box system to attack, maybe your solution is more robust. It may not be giving you the best performance in every case, but it may be more robust, you know, across different channel uncertainties, system uncertainties itself. So white box attack is very specific. In a specific scenario, you should expect a better performance, but it may not translate to general scenarios. So maybe that will be the answer.
So the next question comes from Samhita Kuili. Is a backdoor attack combination of white box and black box attack?
We are talking about the backdoor attack, so Trojan attack. Trojan attack requires you, to, play with the training data. So you need to have the training data, and in the training data, you need to manipulate some data and some features. In that sense, so it is, good for the, white box type of a system. But when you activate the triggers in the later stage, then you do not need to know the, what the attacker will, defender would be doing. So the test site is more towards the black box.
So the next question comes from SKK again. What attack systems, when implemented, allow for the least difference between the original image and the perturbed image? Conversely, what attacks change the original image the most?
Right. So again, like in the image domain, you are dealing with the pixels, right? So you have the math in terms of pixels. So again, so you can try to quantify it, in terms of like a basic differences of the pixels, etc. But one issue with the computer vision domain, changes in particular pixels, etc. Even if you do a lot of changes, it may not translate visually that people will distinguish these changes visually. So therefore, computer vision for community is using different metrics to understand the effects of changes in the images, etc. In our case, in the wireless system, this kind of changes again can be understood. I think we use the norm 2 there, so you can use different norms, to do that. But if your goal is to change the system fully, then you need to set up in a different way. For instance, we have some GAN structure there. In that case, you wanted to distinguish between the real and synthetic. images, right? You can set the real images in a way that is completely different from the real ones that are corresponding, and then you can try to distinguish it from this like a lot of changes as well. I cannot think of one particular application, but it is possible to change one waveform to another. It is possible, but this is also kind of related to the when you make the changes from BPSK to QPSK. You can argue that as you increase the number of the constellations, then you will have more change. So you can try to set the target label from BPSK, let's say, to QPSK. Maybe you can argue that this is like not much a change of the order of the constellation, or you can change it to like a 256 QAM. Then there will be a lot of change. Yeah, I think that you need to, in the wireless domain, probably the changes will be more like operational. So you need to have some kind of like an expert knowledge saying that, hey, this corresponds to a big change.
Right. The next question comes from Muhammad Shojafar. In 5G AML, can GAN model be placed on the core of 5G?
Yeah, in terms of like resources, like you have like a virtual containers, etc., you can put it there. GAN models take some time to train. In the testing time, the generative itself is a one neural network, and you run a test time, so it is not a big deal. But you need to, like, if you want to train in the core, you need to have the necessary resources to do that one. And, you can use it for different purposes. I didn't mention there, one aspect of the GAN is to augment the training data such that you can train the models in a better way. So if the core is getting a lot of traffic data, for instance, or application level data, and if they want to enrich this data so that they can, train or retrain in a better way, yeah, for sure, GAN can be used there as well.
So the next question comes from Ulwasain Ajay. What is the PSR?
Yeah, so let me go through that one a little bit in more detail. I think we talk about the PNR. This is the perturbation to noise ratio, because what we were adding the perturbation to a signal, but we want to compare it to the noise. Later, we had one example on the initial access where we are, manipulating the receive signal strengths, and which includes like the receive signal strengths include the receive signal plus the noise, whatever you see, right? It is including already, and you don't know what is the difference at the receiver, and you are adding a perturbation there. So therefore, you are like your perturbation with respect to the received signal. So perturbation to signal ratio, and S is the received signal if there is no perturbation. Basically, RSS.
Right. So the next question comes from Muhammad Shojafar. Can we use RL reward recovery for both or any one of the attack defense for real-time traffic between 5G G-node Bs?
Yes, I mean, reinforcement learning agent, needs to be running. And the idea is it doesn't have a model, right? It's modelless, and you learn the model sort of over the time. And one way of doing is keep running it. Or you can sort of reduce the runtime. So you can run it for a while and let it go, and then, reduce the number of the updates as well in the algorithm. Yes, I mean, you can run it, in real time as well. And again, in this example, it is in the RAN. It should be, running in RAN or the Mac or something like that. But it can be run in the core as well, to support that one. It's kind of like we are not talking about like a nanosecond or microsecond type of a decision. So they're like a higher, like a little bit like a millisecond, second type of a decision. Therefore, we are emphasizing here, this is like a near real-time intelligent controller. So because in slices, I mean, you can have like a microservices, but they are not necessarily working at the nanoscale, like nanosecond scale.
So the next one is not a question, but this is from Stefan Frisbee saying that very captivating talk. Thank you. And that's true. It's been a wonderful talk with so many interesting points to talk about. The next question comes from Marco Hernandez. Very interesting and timely lecture. Thank you to the speaker and the organizers. Sorry, I thought that this is another question. Yes, it indeed was very interesting. Again, the next one is very nice and prolific talk, Yalin. Many thanks. The next one is also from Kun Wang. Thank you. I think I'm just going to read these quickly and try to find which one. Okay, so this is a real question. Oluwasan Ajayi is asking this question. Can you expatiate on the generator and discriminator network?
Can you say it again? The first one?
I think, can you explain the
Okay.
generator and discriminator network, so the GAN model?
Sure. All right, so here's the example here. So generator network is a neural network. Discriminator network is a neural network. The goal of the generator network is to generate a synthetic data, in our case, spoofed signals. And discriminator network is taking input, some signals. It can be coming from real data, or it can be coming from the synthetic data generated by the generator. And the discriminator is trying to distinguish this. You can consider as a signal classifier. And the generator is also taking as an input as a noise there, so that it can have some randomness to generate the samples. And there is some kind of feedback between the discriminator and generator. So discriminator needs to tell back, whether it's a real or synthetic, so that the generator can adapt to itself. So as the generator is getting better, discriminator needs to get better as well, right? So there's some kind of a game between them, and it is playing some kind of a minimax game played between the generator and discriminator there. And the output of the discriminator is a real or synthetic. Once it is fully trained, generator is generating some signals that are very close to the real one, and discriminator should have a difficulty in discriminating them. Ideally 50%, right?
Yes. The last question that I have so far here is from Jehoshua Hanky Pratama. I believe adversarial attack was introduced in image domain.
Yeah.
How is adversarial attack can be used now in network domain? Is there any huge modification on the attack techniques in order they can attack the network domain?
Yes, I mean, yeah, so that's correct. So I think this was emphasized from the beginning. So computer vision and NLP, communities, as in this example, has been developing these attacks. Yes, there is a differences. And so one difference is, as I mentioned, it is not adding this perturbation. These perturbations are coming from these channels. And those are complex numbers. So not only the strength, but also the phase of the signals is changing. And these phase shifts are very critical, in terms of the INQ data, and can make some BPSK decision just easily flip to the QPSK or something like that. So this kind of effect is very important. And second one is it is possible maybe for a image classifier, send some samples, get labels, send some samples, get labels. In our case, in the wireless, lots of things are done over there. You don't have a direct access to a classifier, right? In 5G RAN case, I mean, nobody will tell me what the RAN is doing. I need to observe over there and learn it. And that's sort of another difference. And I cannot right away also manipulate that input. I need to do it over there, or deal with the other aspects of the mechanisms in the 5G and so on. So those are some fundamental differences. But again, the basic math, is similar, of course, in different cases.
Right. I don't have any more question from the audience, but before we end, I have just maybe a quick question for you. So why do you think it is necessary to train over the air? Is it possible to train with synthetic data and then move to a realistic system? And once we do that, then probably if there are more adversarial attacks, is it easier to handle it that way, because then you'll be able to detect?
Sure. I mean, there are two things. So GAN type of things are useful, like synthetic data, to augment the training data. And you can do it, offline, of course, to augment it, so your training model is different. In this case, we were using it to spoof the signals, right? And of course, you can train the system to all of it in the lab as well. But then there's a problem when we are going to the real system, the channel effects, etc. If they are translating to the new system, then there's no problem. But it may not be possible, right? So therefore, I mean, I think in general, a suggestion, in the community is do something in the offline So bring it to some level so that you don't have too much of a convergence problem. But also sort of like update the system in the real time as well, so that we can also capture the live effects basically.
Right. So in other words, will we be able to detect if there are major changes when it is actually moving from lab setup to the real setup? Because at that point, we would.
That's a great question. I think I didn't mention there. So we did some work a couple of years ago, and I think it was published in ICC or somewhere. So, I mean, the idea is like a GAN, not for only data augmentation, but for data, for domain adaptation as well. So let's say, I, training a classifier for spectrum sensing purposes, and I train it for channels, I mean, using, let's say, Gaussian channels or whatever, like a relay fading channels. But let's say some parameters of these channels are changing, the SNR is changing, or like a relay fading coefficient. So whether you can, do this using the GAN to, adapt the domain. The answer, at least for this simple setting, yes, it can help, but I think more work needs to be done. So GAN is very, powerful for like a domain adaptation. And again, from the computer vision community, there are some examples like a cycle GAN and so on to help with that. I think, again, it will be useful. But again, the signals we are dealing with is way more complicated. So we are not dealing with discrete pixels with a, like a very close, like a very specific spatial correlation. We are dealing with like a lot of effects, channels, interference, traffic, sharing, etc.
Sure.
So Yalin, I had one quick question about your way of tricking the attacker, basically fooling the attacker by allowing some, or rather denying some legit users access.
Yeah.
So I was just thinking, if that is your strategy, and that is a good strategy, because it would not make too much sense to try and allow those who are not authorized in an attempt to fool the system, because the cost could be too much. So if one knows that this kind of bias exists in the way that you might try to trick the attacker, then couldn't the attacker kind of try and do something?
Sure.
To use that information, like a side information, to try and get smarter about the attack? Sure.
So that's a very good point. So the main concept of fooling the adversary is that, as adversary is fooling the system, because the system's classifier is very sensitive to manipulations. Same way, the adversary is building a surrogate model, a classifier as well, and that one will be sensitive to errors as well. So therefore, you want to fool that one back. And again, that's a very good point. There's some kind of a game between them. So one fools the other fools the other as well. So, and it will be interesting to look, whether they can come to some kind of equilibrium, in terms of the attack and defense space. Yeah.
Yeah.
So maybe it can go to game theory as well.
Yeah.
Great. Thank you, Yalin. Thank you, Yalin. This was a wonderful talk, a lot of information, and very, very interesting. So from all of the audience's perspective, I would like to thank you, and thanks.
Thank you,
and
Dola,
we'd like
thank
to
you,
get
Suba.
the slides if possible.
Yeah, I will send it. And before finishing, I also want to sort of put a quick advertisement about a workshop we are organizing. This is not an IEEE, it's an ICM, but very similar, in the context of wireless security and machine learning. And I believe Suba is one of the persons who helped us in the past in that. So the deadline is coming up, and so we are expecting your papers in this domain. Thank you.
Thanks.
Thanks.
Thank you. Bye.
Bye.